Welcome students to today's lecture on the continuation of discussion on experimental aspects of nuclear astrophysics. In the previous lecture, I have discussed in brief ionization chambers, characteristics of gas filled ionization detectors, organic scintillation detectors, starting from the history of spin theory. In today's lecture, I will continue the discussion on nuclear radiation detectors, mainly inorganic scintillators and semiconductor detectors, and I will summarize by comparing with the ionization chambers. And if time permits, I will discuss one of the experimental techniques to measure the nuclear reaction cross section. All right. Yeah. So, here you can see the band diagram for inorganic scintillators. Here we have replaced the medium of detection from gas to solid, though we know that sodium iodide doped with thallium was in use since 1940. Actually, the renaissance began in mid 1980s and still it continues. So, in inorganic scintillation crystals, when transition take place from conduction band to valence band, then the emission of photons is not an efficient process. That is the reason activators are used to dope inside the crystal. Okay? And the activators, they sit in between conduction and valence band as activator excited states. Because of this, electrons from conduction band to the activator states and holes from the valence band, the recombination leads to the emission of photons. So, we have activator ground states, we have activator excited states. The transition gives rise to the emission of photons, which is an efficient scintillation process. So, without the presence of activators, many a times it is not required always. For example, if you take cerium bromide, and there are a few scintillators which does not require any kind of activators, but most of the times in the field of inorganic scintillators, it is important to dope with activators, which makes the emission of photons during the recombination of electrons and holes in the visible region. And this visible region, the optical photons, that means photons in the visible region, they can be easily sensed with a photosensor like photomultiplier tube, silicon photomultiplier or avalanche photodiode. There are many photosensors. So, the basic principle of inorganic scintillator is explained in this slide. Okay. Now, the optical photons emitted from this crystal have to be coupled to an efficient photosensor. What kind of photosensors have to be used? For example, the widely used photosensors are bialkali photomultiplier tube, and if you see the spectral sensitivity of the PMT on the y axis, wavelength on x axis, there should be an agreement or matching between the wavelength of the maximum wavelength of the photons emitted by the scintillation crystal and the wavelength, maximum wavelength for which the PMT spectral sensitivity is maximum. Okay? The wavelength for which PMT has maximum sensitivity, then we can have a better combination as a detector. So, it is important to choose an appropriate photomultiplier tube. In this diagram for various detectors, for example, in this diagram you can also see the cesium iodide whose maximum wavelength is about 550. So, for this bialkali PMT is not very much suggested, whereas for this sodium iodide, if you see the sodium iodide emits photons whose wavelength is varying like this, and the maximum wavelength is around 420 nanometers, and even for bialkali method, bialkali PMTs, the maximum wavelength is about 420 nanometers. So, that is where, this is how one has to choose the photomultiplier tube for efficient detection of optical photons emitted by a scintillation crystal. So, the combination of crystal and PMT plays very important role for its use in measuring the nuclear radiation emitted during the nuclear reaction relevant for astrophysics. All right. And the advantage of inorganic scintillators is because of its high density, the light yield is really good, it is much better than organic scintillators, and many a times you will also come across fast decay time. And the mechanism of scintillation depends on the energy states determined by the crystal lattice. For example, if the energy states determined by the crystal lattice, if they allow, then there is no need of any activators. Whereas, in the case of sodium iodide, if you see, thallium doped is very much required. And in the pure crystal, as I said, the emission of photon is an inefficient process. That is why role of activators comes into picture. That means impurities are deliberately added, which act as the luminescence centers. So, basically these are called luminescence centers, because they are causing the emission of light. And if you see the value of W, that means energy required to create one electron hole pair, normally on average it is 3 times the band gap. Remaining energy goes into the non-transitional processes. So, that is the reason we see the W value of inorganic scintillators is much higher than the semiconductor detector, and it is of the order of W value in the case of ionization chambers. And in order to use light emitted by this scintillator, as I said, the spectrum should fall near the wavelength region of the maximum sensitivity for the device used to detect the optical photons. All right. Let me quickly provide you the basic information of sodium iodide doped with thallium, because it is widely used detector in the field of nuclear astrophysics. So, it is important for you to understand the role of activators and the role of sodium iodide doped with thallium. What are the properties which makes them useful for studying the nuclear reaction measurements. Okay. So, in 1948, Hofstadter he demonstrated that the crystalline sodium iodide, in which a small amount of thallium iodide, where iodine is mainly responsible for the interaction with the gamma rays, it has been added in the melt, and this thallium iodide plays role not only for the iodine, but the thallium acts as a activator. So, that light emitted from the crystal comes into the visible range. Okay. And when thallium iodide is added to sodium iodide, Hofstadter has seen that the light output is really good when compared with the organic materials, and even now the sodium iodide doped with thallium is dominant because of its low cost. That is one of the main reasons, and the time tested sodium iodide detector is still under use because of the reasons like low cost and ability to grow in different sizes and shapes. You can grow into straight, conical, hexagonal, and different shapes one can get using crystal growth methods like Bridgman method, all right, and low cost, large volume, because large volume crystal is useful for the detection of high energy gamma rays. However, it is hygroscopic, one has to pack the crystal within some material like aluminum, otherwise it will go bad, and the light yield is about 38,000 photons per MeV. Okay. And the decay time is not excellent, but it is perfectly all right, 230 nanoseconds, and the energy resolution is about 6%. So, whenever I quote any number for energy resolution, so it has to be understood that it is for 6:2 keV emitted by cesium-137 nucleus. In one of the previous lectures, I have explained the decay scheme of widely used gamma source, that is cesium-137. Fine. So, energy resolution of a detector, when it is mentioned, unless energy is mentioned otherwise, it corresponds to the energy of 6:2 keV, because energy resolution is strong dependent of gamma energy. So, with change in energy, energy resolution also changes. So, whenever you come across energy resolution value, it corresponds to the 6:2 keV gamma rays. Significant non-proportionality. So, when I say non-proportionality, it means the relation between the number of photons emitted and the amount of energy deposited. Because of various reasons, it is not proportional always. So, this non-proportionality is significant in the case of sodium iodide, mainly at low energies. Okay. So, it is not very much important for us, because the gamma rays of our interest, they are above 1 MeV kind of thing. And this diagram shows the variation of light output versus electron energy. Now, you can ask a question. This inorganic scintillator is mainly used for the gamma rays, because it is hygroscopic and we are encasing inside some metal. It cannot be used for the detection of charged particles, and it is not very sensitive for the neutrons as well. So, mainly it is used for gamma rays. So, if I want to show the variation of light output, it has to be with respect to the gamma rays. Why it is electron? Not very difficult to get the answer. So, gamma rays interacts with matter. It could be gas, liquid or solid via 3 processes, as I said in the previous class: photoelectric effect, Compton and pair production. And the outcome in all these 3 processes is electron. So, the energy of the gamma is transferred to the electron fully or partially, and it is the traversal of electron in the crystal which is responsible for the production of scintillations. It is the passage of the electron within the crystal. This electron is coming from the gamma ray, which has transferred its energy partially or fully to the electron, to the bound or loosely bound electron in the crystal. So, this electron, while losing its energy, it creates further electrons and holes whose recombination gives rise to the emission of optical photons. So, that is the reason on the x axis I have plotted the electron energy, and you can see mainly in the low energy like 1 to say 100 keV, the non-proportionality is very high, and after 100 keV or say 300-400 keV, the non-proportionality is not very significant. And for crystals other than sodium iodide, cesium iodide, you can see the relative output, how they are changing from 1 to 1000 keV. So, the non-proportionality is prominent in the case of sodium iodide and cesium iodide, especially at the lower energies of electrons. Now, this slide shows you one of the advanced scintillation detectors, that is lanthanum halides. They have very good density like 5.08 grams per centimeter cube, and the yield is about 60,000. See, sodium iodide has about 36,000 photons per MeV. So, in this case it is about 60,000 photons per MeV, and it is very much resistant with respect to the temperature, and mechanical strength is also very good. And this figure shows the comparison between barium fluoride, sodium iodide, of course doped with thallium, and lanthanum bromide. So, the ability to separate 2 peaks. So, here the energy is keV. So, it is 1173 keV and this is 1332 keV. So, the source used here is cobalt 60, whose decay scheme I have explained in the one of the previous lectures. So, cobalt 60 is another widely used gamma source in the laboratory, which emits 2 gamma rays in the cascade. Of course, sometimes we are interested in measuring the angular correlation between these 2 gamma rays as well. All right. But here in the spectrum of barium fluoride, sodium iodide and lanthanum bromide, you can see lanthanum bromide supersedes sodium iodide, which supersedes barium fluoride. So, the advantage of barium fluoride is basically it has a high density. So, its efficiency is higher than the sodium iodide, but resolution is very poor. So, depending on the application, the choice of scintillation detector comes into picture. Okay? And this diagram shows the internal radioactivity of lanthanum bromide. Internal radioactivity of lanthanum bromide. So, as I said, the contaminants like actinium, they emit alpha and gamma rays, especially around 1.4 MeV and in this region and beyond 1.4 also. So, this radioactivity from the contaminants present inside the lanthanum bromide crystal becomes a significant source of background. So, one has to take care of this background as well, even though the detector is shielded properly. So, presently the sizes available for lanthanum bromide is like 3.5 inch diameter and 6 inch. So, beyond this, because of the anisotropy related properties, it is difficult to grow the crystals in large size. So, that is one of the disadvantages of lanthanum bromide to have in large volumes, whereas sodium iodide can be grown in large volumes, but it suffers from the light yield and so resolution and also efficiency. So, as I said, high density, effective atomic number is also quite good, and yield and energy resolution for the small lanthanum bromide crystal, people have reported a resolution of 2.6%. So, see, the resolution of sodium iodide is about 6%, and so for lanthanum bromide it is about 2.6 to 3.2%. So, there is a factor of 2 in terms of energy resolution. Okay? And as I said, internal radioactivity is a big concern, and crystal growth challenges are there for growing them in large size. So, there are lots of materials in the market. There is a trade off between cost, timing, efficiency and the resolution, and there is a theoretical limit. No crystal could reach the theoretical limit like lanthanum bromide, which little bit comes to this theoretical limit, and lanthanum chloride, and one crystal is there YaLO3Ce. This comes after certain conditions close to the theoretical limit in terms of resolution. So, now this photomultiplier tube is basically the conversion of optical photons into signal, electrical signal. Okay? How it works? So, this incident light falls on the photocathode and it converts into strong electric signal by multiplying the electrons, and here at the photocathode the conversion is taking place with the help of photoelectric effect and sensitive to radiant energy in UV, visible and near IR regions. Okay? And outer boundary of this PMT is made of glass for maintaining the vacuum condition, and the amplification is linear, and the uniformity of photocathode also plays important role, and quantum efficiency is not 100%, it is 20 to 30%, and there are reasons for not having 100%. Please guess why photocathode cannot convert the optical photons to electrons fully, and the W is higher than in the gas filled and semiconductor detector. Now, let me discuss the response of scintillation detectors for gamma rays. Okay? And as you know, photoelectric absorption predominates for low energy gamma rays, say up to several hundred keV, and if you go to high energy, say above 5 to 5 MeV, pair production comes into picture, and in between these two ranges you have Compton scattering, and the role of atomic number is very well known of the interaction medium on the relative probabilities of these interactions. So, for a photoelectric effect, element with high Z is preferred. Okay? So, element with high atomic number possess high photoelectric effect probability, because it is given as Z to the power of 4.5. Okay? So, this is the reason high Z materials are preferred for allowing the photoelectric effect to happen when gamma rays interacts with those materials. So, here you can see incident photon ejects the electron. So, I am discussing the interaction of gamma with matter in detail, and here you can see the energy deposited is h nu. So, if it happens with a large number, then dN by dE completely occupied with h nu only. But if it is Compton scattering and applying conservation of energy and momentum, one can derive the energy of the scattered gamma and recoil electron, and the energy of the scattered gamma ray is given by this relation, well known relation, and the range of energies of electrons from theta is equal to 0 to theta is equal to pi gives rise to curve called as Compton continuum, and the edge is called as the Compton edge, and h nu is the place where full energy deposition take place, and the energy of the Compton scattered gamma ray is given here, and energy of the recoil electron is given here. One can easily derive by applying the conservation of energy and momentum. All right. And in pair production, you know, the energy of the electron and positron should be in such a way that it is equal to the incident energy minus 2 511 keV gamma rays. All right. So, that is the reason you will get a peak which is left to the full energy by an amount of 2 m naught c square. This is also called as double escape peak. Okay? And let me quickly explain the predicted response functions of the detectors for gamma rays and neutrons. Because in nuclear astrophysics, many a times the proton capture reactions or neutron capture reactions leads to the emission of gamma rays. So, these gamma rays are mainly detected by scintillation detectors, in particular sodium iodide, and nowadays lanthanum bromide, cerium bromide detectors, they are also in use. Other than scintillation detectors, it is the semiconductor detector which is in use. So, how scintillation detectors respond to the gamma rays? Let me start by assuming different sizes of scintillation detectors. So, let me start from small to large and then intermediate. So, here we need to take into account all physics processes which are happening in the crystal when gamma ray interacts with it. Alright. For example, if you take a size of say 1 inch by 1 inch cylindrical detector or 2 inch by 2 inch cylindrical detector, of course, that is small compared with the mean free path of the secondary gamma rays, which are normally emitted in the Compton scattering and pair production, because pair production we have 511 kV gamma rays, right. Okay, so, this diagram shows you the small size detector in which the h nu gamma photon can undergo photoelectric effect. This gamma can undergo Compton scattering, and Compton scattering can happen once or more than once. So, in single Compton scattering, it is undergoing scattering only once, and the gamma ray which is undergoing scattering is escaping from the crystal. So, that is what I mean by single Compton scattering. Alright. So, here you have recoil electron and this gamma is escaping from the crystal. So, this same gamma, if at all undergoes pair production, you have electron and you have positron, and this emits 511 kV gamma rays in both directions. So, this we are calling as escaping annihilation photons. And here the response of the crystal, if it is less than the 2 m naught c square and more than 2 m naught c square, one should be able to draw the spectrum. So, when I say energy spectrum, what does it mean? It is the distribution of energies of the gamma rays. So, when I say spectrum, it is the distribution of energies. So, energies on the y axis and the number of gamma rays on the x axis. Okay? So, it is otherwise. So, energy of the gamma ray on the x axis and the number of gamma rays with that particular energy on y axis, this dN by dE. And in case the energy of the gamma ray is much more than the 2 m naught c square, so pair production take place and you can expect double escape peak. You can always ask why not single escape peak? Of course, it can happen, but here we are assuming that detector size is small. So, the absorption of 511 kV gamma within the crystal we are ignoring. So, in this slide if you see, two gamma rays are escaping, gamma 1 and gamma 2, whose energy is 511 kV, 511 kV. So, this energy you are losing. So, this double escape peak is happening h nu minus 2 m naught c square. So, continuing this for intermediate size. So, photoelectric absorption as it is, okay, and the Compton scattering happens in such a way that first Compton scattering happening here and second Compton scattering happening here. So, multiple Compton scattering happening here, and overall they are absorbed within the crystal, alright. And sometimes due to multiple Compton scattering also, the final gamma ray can escape, alright. And in the pair production, sometimes the electron and positron, when they are produced, one 511 kV can escape from the crystal, another 511 kV can be absorbed within the crystal. Considering all these processes, what kind of spectrum we can assume? See, remember, in this particular case, in pair production, one 511 kV is absorbed. Why? Because the size we are assuming as bigger than in the previous case, and due to multiple Compton scattering also, we have increased the probability for full absorption of energy. All right. So, here you have single escape peak and also double escape peak. So, in single escape peak we are assuming one gamma rays escaping, and in double escape we are assuming 2 gamma rays are escaping because of the pair production. And now you can see here multiple Compton events. So, there is a difference here I am drawing like this. Okay. So, what is this? Because of the multiple Compton scattering, so other than theta is equal to pi, energy corresponding to theta is equal to pi, if it undergoes Compton scattering again, it can deposit more energy, and that comes in between Compton edge and full energy peak. And due to multiple Compton scattering, if full energy is deposited like in installment, but full energy is deposited, it comes under the photo peak. So, now this peak is no more because of the photoelectric effect. It could be due to the it could be due to the multiple Compton scattering also. So, it makes sense to use the word full energy peak instead of photo peak, because photo peak normally it refers to the peak arising due to the photoelectric absorption only. So, it is always better to use the word full energy absorption peak when you are aware that the crystal size is enough to accommodate the multiple Compton scattering. All right. Now, if I go to the large size detectors, you see nothing is escaping from the detector. Many times it can happen. In the nuclear reaction, if the gamma rays of interest is less, and if you have enough money and if you buy large size crystals, so you are not allowing the gamma rays to escape from the crystal, then what kind of spectrum you expect? See, in photoelectric absorption, in Compton scattering, in pair production, in all manners, whatever electrons and positrons are emitted and whatever further interactions are taking place, nothing is escaping from the crystal. So, full energy is deposited by each gamma ray within the crystal. So, it is quite easy to expect the shape of the spectrum in this case. Okay. So, we can get full energy peak at the energy corresponding to the incident gamma, the energy corresponding to the incident gamma ray. Okay. Now, here I have not included in all these slides, I have not included the energy resolution. Just for the sake of simplicity, I wanted to highlight the effect of size of the crystal on the response of the crystal for gamma rays. So, that is what I am trying to explain in these slides. Fine. So, as I said, let us go for full energy peak, because not only photoelectric effect, you have multiple Compton scattering also, and you have pair production also. It is giving rise to the emission of 511 kV gamma rays, which are again deposited within the crystal. Okay. Now, one of the important aspect of the experimental setup, how the surrounding materials will influence the response of the detector. For example, if you consider here some say source, it could be due to nuclear reaction, it could be due to target or simple radioactive source in the laboratory like cesium, cobalt, sodium. When gamma rays are emitted in all directions, okay, and they are also falling on the surrounding materials surrounding the detector. So, there is a high chance that they undergo absorption within the surrounding material, and they can emit the characteristic X-ray because of the photoelectric effect, and this X-ray can enter the detector, and this detector will detect the X-ray, and this gamma ray, it can pierce through the detector because most of the atom is empty, remember. So, sometimes electromagnetic radiation may not deposit any energy in the crystal and go to the surrounding material, undergoes Compton scattering, and scattered gamma ray can come back to the detector. So, all these scenarios are possible, and if the energy is sufficiently high, it can undergo pair production within the surrounding material, and it can emit annihilation photons, and these photons can enter into the detector. So, there is always a good possibility that detector detects the radiation not only from the source, but also the radiation emitted by the surrounding materials. So, if you plot peak energy photon energy versus scattering angle at different energies. You can see that at higher angles the value of the scattered energy is almost constant. All right. Now, you can see here the spectrum looks something like this. You can have X-ray peak corresponds to characteristic X-ray peak, and backscatter peak because of this Compton scattering, okay, and annihilation peak because of this annihilation photons. So, this is how the materials surrounding the detector can influence the response of the detector. Now, let me discuss the response to neutrons. How neutrons interact with matter. So, we have seen charged particles interacts with matter via ionization and excitation, that is Coulombic interaction. Gamma rays being electromagnetic in nature, they cannot take part in Coulombic interaction. So, electromagnetic interaction covers photoelectric, Compton and pair production mainly. But neutrons, they have mass, but they have no charge. So, what kind of interaction neutrons will have with matter? We can divide into two types. Number 1, scattering, it could be elastic or inelastic. Number 2, absorption. Do you remember nuclear fission process in which slow neutron gets absorbed by uranium 235 nucleus, and you have uranium 236 compound nucleus? Just by absorbing one neutron, U-236 is undergoing fission. It is disintegrating. You have fragmentation. So much is the effect of one slow neutron on a few nuclei like uranium 235. So, the absorption of neutron may lead to the fission, and sometimes the absorption may lead to the emission of neutrons, one or more than one. Sometimes the absorption may lead to the emission of charged particles, and sometimes the absorption may lead to the emission of gamma ray. All right. Because neutron induced reactions are important in the nuclear astrophysics, already have discussed. So, it is important to study those reactions which emit the neutrons and who get moderated and initiate reactions for the synthesis of elements beyond iron peak. All right. So, if you want to understand the nuclear reactions which are emitting neutrons, then you need to use the detectors for detection and measurement of the neutrons. What kind of detectors you use? As I said, it participates in scattering and absorption. So, you take those materials which have high absorption cross section or which have high scattering cross sections. High absorption cross section and high scattering cross section. So, let me give you a few examples. So, as I said, a target nucleus plus neutron can give rise to recoil nucleus as part of scattering, and it can give rise to proton, that means NP, and sometimes it can emit N alpha, and also it can emit neutrons also. So, it can emit N, N2N, okay, and fission fragments, and in this fission fragments also many times you will get the emission of N and gamma. Fine. So, the distribution of neutrons energies versus energy, if you see, it is strongly influenced by the reaction Q value, because the kind of reaction I have explained, it shows that the pulse height happens which depends on the reaction Q value. For example, boron has very good thermal neutron, it is a very good absorption cross section for neutrons. See, when I say neutrons, in general you should be in a position to divide into two types like thermal neutrons and fast neutrons. And the materials which are good for the detection of fast neutrons, most probably they are not good for the detection of thermal neutrons, because the change in the energy when we go from slow to fast neutrons changes the cross section value as well. Fine. So, in this particular case I am discussing one of the important neutron absorber, that is boron. It gives alpha particles of two different energies, okay, and you detect these alpha particles. So, you can see here 2.31 and you can see 2.792. So, dN by dE number of neutrons per unit energy, and reaction product full energy peaks for excited state of lithium 7 gives rise to 2.31, and if the compound nucleus formed because of neutron plus boron 10 leads to the decays to the ground state of compound nucleus, it gives rise to this 2.79 alpha particle. So, the detection of alpha particle is helping us to detect the neutrons. So, it is indirect measurement. So, even gamma rays also, gamma rays they are transferring their energy to the electrons, and electrons are charged particles, and I have already discussed how charged particles interact with matter. Even in the case of neutrons, if they emit charged particles, again this interaction of charged particle with matter comes into picture, all right. And another nucleus which is a good absorption, which has good absorption cross section for neutron is lithium 6, which emits alpha particle, and here the Q value is quite high, 4.78 MeV, all right. And neutron plus helium, one of the important component for the detection of neutrons, mainly thermal neutrons. It gives recoil protons, and by measuring the recoil protons we will get the signal, and boron, lithium, helium, and nowadays people are using gadolinium, all right. So, all these are very good detectors for the thermal neutrons, and for fast neutrons the widely used component is chlorine, which has very good absorption cross section for the fast neutrons. Now, let me discuss the concept of energy resolution, one of the important properties of detectors. See, incident energy, if it is E, and energy required to produce one electron hole pair or one electron ion pair is W, you can find out the number of charge carriers. Number of charge carriers. See, because of the random energy losses, though the incident particle has same energy, because of the difference in the energy loss mechanisms, there is a randomness in the energy loss that leads to the fluctuations in the number of electron hole pairs or number of electron ion pairs produced. See, remember, this is the number small n which plays important role in measurement of the energy, all right. Okay. So, as normally n is very large, so the statistical fluctuation can be approximated by Gaussian distribution with full width half maximum given by 2.35 square root of small n. And because energy is a function, this n is function of energy, so fractional energy resolution is nothing but fractional value in terms of delta n, and delta n is nothing but delta 2.35 square root of n divided by small n, which gives rise to square root in the denominator, and it gives rise to 2.35 W by E. Where from this F comes into picture? This is called as Fano factor. See, Fano has demonstrated that whatever the fluctuations we are expecting in the number of charge carriers, in reality it is not that much, it is less. So, it is less than or equal to 1. Okay. For example, if you go to the gases like argon, it is like 0.4, and for semiconductor it is 0.1. Here you see Fano factor is 0.1 for semiconductors and 0.4 for the gas. So, this less value of the semiconductor also is an advantage for the semiconductor. How? I will discuss in the next slide. Okay. And the generation of the charge carriers, transport of the charge carriers, and efficient collection of the charge carriers plays important role in designing the detector. For example, in case of silicon, normally the sizes are not in centimeters. It's you can see it is of the order of microns to several mm, because it has a less intrinsic conductivity because of the band gap 1.1 electron volts. It can be used at room temperature, because at room temperature the energy is not sufficient for the electrons to go to the conduction band. Okay. So, which is not possible with the germanium because of its less band gap. That is why it is important to cool the detector with liquid nitrogen. So, that is the reason we go for high purity germanium detectors. Okay. So, let us discuss more about the semiconductor detectors. So, the density is of course higher than the ionization chambers. So, I am comparing with now ionization chambers, gas filled detectors. Okay. So, because of the high density, the stopping power is also good, that means dE by dx, the energy loss per unit length is also quite high. So, the range is very small. So, one can have small size detectors and there is a possibility to go for small target chamber. So, that in target when the incident beam reacts with the target material, you can keep the charged particle detectors. Of course, vacuum has to be created within the target chamber. So, because of the range, small value of the range of the charged particle. Now, I am discussing about the importance of semiconductor detectors for charged particles, all right. So, unlike gas filled detectors, there is no need of entrance window. So, this is where the straggling within the entrance window can be avoided. And as I said, the generation, transport and collection of charge carriers efficiently decides the efficient generation, transport and collection decides the sizes of the detectors. And of course, this is some kind of repetition, the silicon and HPG already have discussed this. Now, this is important, the small value of W, okay, it is of the order of 3 electron volts in case of semiconductors. Do you remember the value of W in the case of gas? It is about 30 electron volts. So, 10 times difference. So, W value is less. So, E by W if you take, N will be more. Okay. So, more charge carriers are created and under the influence of electric field and because of the less size, there will be efficient collection of the charge carriers. All right. This gives rise to the value that we are looking for, excellent resolution in terms of energy. For 5 MeV alpha particle, the energy resolution is of the order of 11 keV. And the time resolution also quite good for semiconductor detector, that is the 9 nanosecond. Dead time, particles are continuously falling on the detector. So, before second particle interacts with the detector active volume, sometimes the detector will die for some time, during which it cannot consider the second event. So, this is called as dead time. The dead time is quite high in the case of gas filled detectors, whereas in the case of semiconductor detectors it is quite less, and because of this reason coincidence experiments prefer the use of semiconductor detectors. One of the interesting thing is that semiconductor detectors cannot detect the neutrons, they are insensitive. However, the major problem is neutrons can damage the crystal by changing the crystal properties and inducing the lattice defects. So, if you are using the semiconductor detectors, ensure that neutron sources should not be in the surroundings, all right. And another semiconductor detector, that is germanium, widely used detector for nuclear astrophysics studies is germanium doped with lithium, and another way is you cool the germanium crystal with to low temperature using liquid nitrogen, and this is one of the widely used detector for studying the nuclear reactions with the measurement of gamma rays because of its excellent resolution. Nobody can match HPGE in terms of energy resolution. Why energy resolution is very high in the case of germanium? Because of less W value, okay, and less Fano factor value. And why we need to cool the germanium detectors? Because at room temperature the thermal fluctuations can induce the noise, because of which the data that we want to acquire will be polluted. So, it is very important to cool the germanium detectors, all right. So, with this let me close today's lecture and let me discuss one interesting experimental technique in the next lecture. Thank you very much for your attention.